Today we're going to talk a little bit about the base 2 numeral system. We'll look at converting from our decimal system to binary. We'll also look at addition, subtraction, multiplication, and division in base 2. The numeral system that we're familiar with is called base 10. In base 10, we have the following allowable digits. 0 through 9. In binary, or base 2, our allowable digits are 0 and 1. Let's suppose that we'd like to convert a number from decimal, or base 10 form, to binary, or base 2. Let's convert the number 27 to binary, or base 2. In order to convert a number in decimal form to binary form, what we'll do is we'll begin by taking our decimal number, 27, and dividing by our base, which is 2. 2 goes into 27 13 times, with a remainder of 1. The process of converting from decimal to binary relies on us keeping careful track of our remainders. So I'll circle our first one. Next, we'll divide 2 into our previous quotient, 13. 2 goes into 13 6 times, with a remainder of 1. Continuing the process, 2 divides into 6 3 times, with a remainder of 0. Then 2 divides into 3 1 time, with a remainder of 1. And finally, 2 divides into 1 0 times, with a remainder of 1. Now I'll look at my remainders, beginning with our most recent and tracking back to the first one. So we have a remainder of 1, 1, 0, 1, 1. Therefore, the decimal number 27 is equivalent to 11011 in base 2. Let's talk about addition in base 2. Suppose I had two binary numbers and I wanted to add them together. 10111010 plus 11011. We'll perform this process in essentially the same way we would work a problem in decimal form. If we look at addition in decimal form, the process is almost second nature. After all, most of us have been doing this for most of our lives. Let's suppose we have 392 plus 131. If I wanted to add these two numbers together, I know that 2 plus 1 equals 3, and I know that 9 plus 3 equals 12. But we don't write 12 here. We all know that we need to carry a group of 10. And so what we do is we carry a 10, and we write the remainder 2. Then finally, we have 1, which is our carried 10. Now in the hundreds place, 1 plus 3 plus 1 equals 5. And so we know that 392 plus 131 is equal to 523. We use a similar process for base 2. However, in this case, anytime we have a sum of 2, since 2 is like our 10 in decimal form, anytime we have a sum of 2, we're going to carry the 2 as a 1. For example, 0 plus 1 is 1. Now 1 plus 1 is 2, but since we're working in base 2, our only allowable digits are 0 and 1. 1 plus 1 is 2. We carry the group of 2 as a 1, and we have 0 left over. Continuing on, 1 plus 0 equals 1. And now we have 1 plus 1, which is 2. We carry the group of 2, the remainder of 0. And now we have 1 plus 1 plus 1. 1 plus 1 is 2. So we carry, and we have 1 left over. Now 1 plus 0 is 1. And finally, we carry down a 1. Therefore, the sum of our two binary numbers is 1110101. If we wish to subtract two numbers in base 2, we employ a similar process. For example, suppose we have 110 minus 11. Beginning with the column furthest to the right, we have 0 minus 1, and it's going to be necessary for us to borrow a group of 2. So here, I borrow a group of 2. Now we have essentially 2 minus 1, which equals 1. And proceeding to our middle column, since we borrowed a group of 2, now we have 0 minus 1. Again, we're going to have to borrow another group of 2. 2 minus 1 equals 1. Therefore, 110 minus 11 equals 11. Let's take a look at a multiplication problem in base 2. Suppose we have 111 times 11. Again, we'll proceed with the multiplication process just like we would in a base 10 problem. However, instead of carrying groups of 10, we'll be carrying groups of 2 when it becomes necessary. So let's get started. 1 times 1 equals 1, and then 1 times 1 equals 1, 1 times 1 equals 1. Now, just like we would in ordinary multiplication, we'll start our second row from the right with a 0, and again we'll have 1 times 1, 1 times 1, and 1 times 1. Next, we'll sum our two rows. So we have 1 plus 0, which is 1. Now 1 plus 1, which is 2. That means that we have to carry a group of 2, and we have a remainder of 0. now we have 1 plus 1 plus 1. So in other words, we have a group of 2 to carry with 1 left over. Then we have 1 plus 1, which is a group of 2. So we're going to write the remainder as 0 and carry that final group of 2. So we have 1, 1, 1 times 1, 1 equals 1, 0, 1, 0, 1. Let's take a look at division in base 2. Here we see that 1, 1 can't divide into 1 or 1, 0, but 1, 1 can divide into 1, 0, 1 one time. So now we have 1, 0, 1 minus 1, 1. 1 minus 1 is 0. Here we have to carry a 2. 2 minus 1 is 1. Now we carry down a 0. 1, 1 goes into 1, 0, 0 one time. Starting furthest from the left, we have to borrow our groups of 2. Carrying our last one, 1, 1 divides into 1, 1 one time. Now this last step might look a little confusing, but keep in mind that here, when we carry our groups of 2, we don't really have 0 minus 1. It's really 1 minus 1, leaving us with 0. Similar to the way in base 10, if we had 100 minus 99, we would continue to carry until we got our end result. 100 minus 99 equals 1. So in this case, 1, 0, 1, 0, 1 divided by 1, 1 equals 1, 1, 1. So this concludes our example of base 2 operations. I hope you found it helpful, and we'll see you next time.